children, hearty welcome to today's module. With the previous module, we completed the chapter liquid state. Here we have the question and answer session. I have included some of the indirect questions and answers here and some problems also solved. The first question, explain the major type of intermolecular forces present in HCl and bromine. So let us discuss the intermolecular forces present in HCl first, then we will move on to the intermolecular forces present in bromine. In HCl, the types of forces are, the major intermolecular forces present in HCl is dipole-dipole interaction. HCl is a polar molecule because chlorine is much more electronegative than hydrogen, creating a permanent dipole with a partial positive charge on hydrogen and a partial negative charge on chlorine. The dipole-dipole forces arise from the attraction between these oppositely charged ends of neighboring HCl molecules. So what is discussed here is HCl, this chlorine is highly electronegative and it acquires partial negative charge, and this hydrogen that acquires partial positive charge. Therefore, HCl is polar molecule. And dipole-dipole interaction is more prevalent in HCl. Then in the case of HCl, there is a London dispersion forces also, because all molecules, including the molecules which are having dipole-dipole interactions, also experience London dispersion forces. But in HCl, the dipole-dipole interactions are stronger and dominate. This is about the intermolecular forces of HCl. So answer we have to write like this. In the case of HCl, the most intermolecular forces is dipole-dipole interaction, and how the dipole-dipole interaction happen in the case of HCl, that we have to discuss here for this question. And there will be a chance of London forces, but in the case of HCl, the dipole-dipole forces are strong and dominant. Now let us discuss about the bromine. In the case of bromine, the major intermolecular forces present is London dispersion forces, which is also called van der Waals forces or dispersion forces. We know that bromine is a nonpolar molecule because both the atoms are identical. Here the bromine, both the atoms are identical. Therefore, there is no permanent dipole exist in bromine. The only intermolecular forces acting between bromine molecules are temporary induced dipoles that result from the fluctuations in the electron cloud. So here in the case of bromine, this bromine atom, since the electrons are moving around the nucleus, there is a fluctuations in the electron cloud, and at some point of the time there is a dipole formation is happening in the case of bromine. And that is why here in the case of bromine we have London dispersion forces or van der Waals forces or dispersion forces existing. These London dispersion forces are the weakest type of intermolecular forces but are relatively stronger in bromine because it is a large molecule with many electrons, making it electron cloud highly polarizable. So this is the London dispersion force is present in the case of bromine, and in the case of HCl it is dipole-dipole interaction. So that is the answer of first question. Now we move on to the second question, that is, how do van der Waals forces depend upon temperature? How do van der Waals forces depend upon temperature? That is the question. The answer is, generally the van der Waals forces are independent of temperature. We have some exceptions. So let us discuss this here. Van der Waals forces show varying relationships with the temperature depending on the specific type of intermolecular force. So for most van der Waals forces, they are independent of temperature with some exceptions. So the exception is dipole-dipole interaction. These dipole-dipole interactions are temperature dependent. At higher temperatures, weaken these dipole-dipole forces due to increased molecular motion, while lower temperature enhance them. So how this temperature affects the dipole-dipole interaction? That is, when temperature increases, what will happen? The molecule will gain some kinetic energy. Therefore, the molecular rotation will increase. So since the molecular rotations are increasing, the dipoles have less time to align favorably. Therefore, the effectiveness of dipole-dipole attractions decreases when the temperature increases. So when the temperature increases, what will happen? The molecules gain more kinetic energy, therefore molecular rotation increases. So since the molecular rotations are increasing, the dipole-dipole interactions can happen very easily. Therefore, the effectiveness of dipole-dipole interactions are less, or it is decreasing while increasing the temperature. The practical example for this phenomena is the behavior of water. The behavior of water at 100 degrees Celsius, the kinetic energy of water molecules overcomes the van der Waals forces, and it will allow the water to boil, or it causes water to boil. So at 100 degrees Celsius, the kinetic energy of water molecules overcomes the van der Waals forces, therefore water will boil. But at 0 degrees Celsius, what will happen? The kinetic energy is less. Because of the lower kinetic energy, the intermolecular forces will dominate, which will cause water to freeze. That is the temperature dependent of the dipole-dipole interactions. And other forces which are independent of temperature are dipole-induced dipole interactions. Dipole-induced dipole interactions, they are temperature independent or not temperature dependent. And London dispersion forces, they are also temperature independent or not temperature dependent. Therefore, we have the dipole-dipole interactions that is temperature dependent, but the London forces, or that is instantaneous dipole-induced dipole forces and dipole-induced dipole forces, are temperature independent. That is the answer for the second question. Okay. Now we have the third question, that is, what kind of van der Waals forces exist between HCl and benzene molecules in a system that contains both compounds? Explain your answer. That is the third question. The third question is, what kind of van der Waals forces exist between HCl and benzene molecules in a system that contains both compounds? So when we discuss this, we have to look into the molecules. HCl is polar molecule and benzene is non-polar molecules. Therefore, automatically the van der Waals force will be dipole-induced dipole forces. So now let us see how this dipole and induced dipole forces exist between the HCl and benzene molecule. When we consider the intermolecular forces between benzene and hydrogen chloride, the major van der Waals forces or interactions involved are dipole-induced dipole interactions. Dipole-induced dipole interactions. We know that HCl is a polar molecule because the charge separation is there in the case of HCl. Because chlorine is highly electronegative compared to hydrogen. Because of this permanent dipole moment, this HCl is polar. When we look into the benzene, it is a non-polar molecule with a symmetric electron cloud but highly polarizable due to pi electron system. So benzene, we have to remember that it is a non-polar molecule and the symmetric electron cloud is present in the case of benzene, but it is highly polarizable because of the pi electron system. So benzene structure is like this. So this is benzene. There in the pi electron system is more strong, because of that benzene is highly polarizable, and it is non-polar because of the symmetric electron cloud. Now what will happen when there will be an interaction between the benzene and the HCl molecule? The permanent dipole of the HCl can induce dipole in the benzene molecule by distorting its electron cloud temporarily. The permanent dipole of HCl can induce a dipole in the benzene molecule by distorting its electron cloud temporarily. When the electron cloud is distorting, what will happen? That will lead to dipole-induced dipole interactions. Dipole-induced dipole interactions. So that is a type of van der Waals forces. So between the HCl and benzene molecule, dipole-induced dipole forces are existing. And in the case of HCl and benzene, another type also is there, that is London dispersion force, because this instantaneous dipole and induced dipole interactions are present in all the molecules. Both benzene and HCl molecules experience London dispersion forces, that is instantaneous dipole induced dipole interactions. Okay, this is about the interactions between HCl and benzene molecule, that is mainly dipole induced dipole interaction, because HCl is a dipole, or HCl is having a permanent dipole, and benzene is non-polar molecule. Another force also is there, that is instantaneous dipole induced dipole interactions, because these forces are present in all the molecules, but they are generally weaker compared to dipole induced dipole forces in the case between HCl and benzene molecules. Next question is question number 4. Define coefficient of viscosity. What are its SI unit and CGS unit? The coefficient of viscosity of a liquid is defined as the force per unit area required to maintain unit difference of velocity between two parallel layers unit length apart. That is, when we discussed about the coefficient of viscosity, we saw that the viscosity depends upon the area of the plate, and it is also depend upon the velocity gradient du by dz. So this is eta, that is the viscosity, is directly proportional to A into du by dz. When A is equal to 1 and du by dz is equal to 1, that time what will happen? There we have a constant. That constant is called it as coefficient of viscosity. Okay, here we have the force acting. The force acting will be directly proportional to A, that is the area of the plate, and here also this force which is acting against the viscosity will be directly proportional to the du by ds. D is said, that is the velocity gradient. Therefore, we can write it as the force is directly proportional to A into du by dz. When A is equal to 1, du by dz is equal to 1, there is a proportionality constant, that is coefficient of viscosity. That is coefficient of viscosity. So, what is coefficient of viscosity? The coefficient of viscosity of a liquid is defined as the force per unit area, is defined as the force per unit area required to maintain unit difference of velocity between two parallel layers unit length apart. Also, this coefficient of viscosity is a measure of fluid resistance to flow. The SI unit is Pascal second, that is, we can write it as PAS, small letter S. This P is capital letter PAS. The CGS unit is Poise, that we will write in capital letter P. Okay, 1 Poise is equal to 0.1 Pascal second. 1 Poise is equal to 0.1 Pascal second. Next question, how does viscosity depend upon the cohesive forces in a liquid? How does viscosity depend upon the cohesive forces in a liquid? The explanation is, viscosity is a measure of a liquid's resistance to flow. Viscosity is a measure of a liquid's resistance to flow. It depends directly on the cohesive forces between the molecules in a liquid. We know that the cohesive forces are the attractive forces between molecules of the same substances, attractive forces between molecules of the same substance. And in a liquid, the stronger cohesive forces mean that the molecules stick together more tightly. The molecules stick together more tightly if there is a strong cohesive forces. When cohesive forces are strong, it becomes more difficult for the molecules to slide past each other, resulting in higher viscosity. Conversely, if the cohesive forces are weak, the molecules can move more freely, resulting in lower viscosity. Example, we know that glycerol and honey have strong cohesive forces and therefore they have high viscosity. But in the case of water and alcohol, they have weaker cohesive forces, therefore they have lower viscosity. I hope you understood this question, that is, how does viscosity depend upon the cohesive forces in a liquid? In brief, if the cohesive forces are strong, that substances will be more viscous. If the cohesive forces are weaker, then that compounds will be less viscous. Next question. Water has a high specific heat. Why? Water has a high specific heat. Why? The specific heat capacity is the property that indicates the amount of heat required to raise the temperature of 1 gram of the substance by 1 degree Celsius. This we have discussed in our modules, already discussed in our modules. That is, the specific heat capacity is the property that indicates the amount of heat required to raise the temperature of 1 gram of the substance by 1 degree Celsius. Water has high specific heat capacity compared to most other substances because of the hydrogen bonding between the water molecules. So when we apply heat, this heat will be used to break up the hydrogen bonding between the water molecules and they will move more freely. Since it requires more significant energy input to disrupt, the specific heat capacity is required more. Okay, that is the answer for the high specific heat capacity of water. Water has a high specific heat. Why? Specific heat capacity is required more in the case of water because of the hydrogen bonding. Therefore, initially when we apply heat, what will happen? The hydrogen bond will break. Then only the temperature rise will happen for the 1 gram of the substance. That is why the specific heat capacity is high in the case of water molecule. Next question. Ice has a lower density than liquid water. Ice has a lower density than liquid water. Explain. The answer is ice has a lower density than liquid water because when water freezes, its molecules form a rigid crystalline structure due to hydrogen bonding. When water freezes, it forms a rigid crystalline structure because of the hydrogen bonding. In this structure, the molecules are arranged in a hexagonal lattice. So when water freezes to ice, the molecules are arranged in a hexagonal lattice. In the hexagonal lattice, there will be a large gaps or voids between them. Because of these large gaps and voids, the oleum is high, no? The oleum of the voids and the gaps are high. Density is mass by oleum. Then if the oleum is high, the density will decrease automatically. In the case of liquid state, water molecules are more closely packed and can move freely, resulting in less space between them and thus a higher density. In the case of water, what will happen? The molecules are arranged very closely, therefore there is no space between them, hence the density is high. This unique arrangement is why ice is less dense and that floats on water. Ice is less dense and that floats on water. Next question. Explain the anomalous expansion of water on freezing. Explain the anomalous expansion of water on freezing. Water exhibits a unique behavior known as the anomalous expansion when it freezes, which is unusual compared to most other substances. In normal cooling, that is above 4 degrees Celsius, Normal cooling means that is above 4 degrees Celsius. As water cools from higher temperatures down to 4 degrees Celsius, it contracts and its volume decreases as expected. Therefore, the density increases because the molecules move closer together. That is in normal cooling. When cooling below 4 degrees Celsius, when the temperature drops below 4 degrees Celsius, water starts to expand, its volume increases and its density decreases. So this is the beginning of the anomalous expansion. So anomalous expansion happens when the temperature drops below 4 degrees Celsius. Then when freezing occurs, that is at 0 degrees Celsius, water freezes into ice. During freezing, the water molecules arrange themselves into a rigid open cage-like structure, that is the hexagonal lattice, due to hydrogen bonding. And because of this structure, there will be more empty spaces between molecules than the liquid water. So ice has a higher volume and lower density than liquid water. Why we say that there is an anomalous expansion? That is because most of the substances contract and become denser when they freeze. Most substances contract and become denser when they freeze. Water, however, expands upon freezing, making ice less dense than liquid water. Water, however, expands upon freezing, making ice less dense than liquid water. That is what we say, that there is an anomalous behavior in the case of water. So from this question onwards, we have problems. The question number 9, that is, at 298 Kelvin, liquids X and Y have vapor pressures 13.332 kilopascal and 26.665 kilopascal respectively. The corresponding enthalpies of vaporization are 43.57 kilojoule per mole and 16.74 kilojoule per mole respectively. Calculate the temperature at which both X and Y have the same vapor pressure. So, you have to find out the temperature at which both X and Y have the same vapor pressure. So, this problem is little tricky, but it is quite interesting also. Here, the P1 is 13.332 kilopascal, P2 is 26.665 kilopascal, and the X and Y are the liquids. So, the heat of vaporization of X is given as 43.57 kilojoule per mole and the heat of vaporization of Y is given as 16.74 kilojoule per mole. And we have to find out the temperature at which both the X and Y have the same vapor pressure. We have the equation, that is the Cauchy-Clapeyron equation. Ln P is equal to minus delta HV by R into 1 by T plus C. So, we have the two liquids X and Y. For the X, this equation becomes ln P1 is equal to minus delta HY by R into 1 by T plus Cx. C is the constant. Then for the second liquids, that is for liquid Y, we have ln P2 is equal to minus delta HY by R into 1 by T plus Cy. At a temperature T, vapor pressures are equal. That is the condition. That means Here, since these sides are equal, these vapor pressures are equal, we apply the condition, this side also will be equal. Therefore, vapor pressures are equal means the P1 and P1 is equal to P2 is equal to P. So that is the condition. So if that is the condition, minus delta Hx by R into 1 by T plus Cx is equal to minus delta Hy by R into 1 by T plus Cy. Okay, here if when this minus delta Hy by R comes here, it will be positive. That is delta Hy minus delta Hx divided by R into 1 by T is equal to Cy minus Cx. This Cx will come this side, therefore the negative side. So now we have to find out at 298 Kelvin, what is Cx and Cy, that we have to find out. For that, ln P1 is equal to minus delta H by R into 1 by T1 plus Cx. So we are substituting all the values here. Ln 13.332 into here, that is kilopascal. So when it converts into Pascal, we multiply with a 10 power 3. Here the delta H vaporization is minus 43.57 into 10 power 3 joule per mole. In the question it was given in kilojoule per mole. Here we converted that into joule per mole by multiplying with the 10 power 3 divided by 8.314 joule per Kelvin per mole into 1 by 298 Kelvin plus Cx. Therefore, when we arrange this equation, that is Cx here, then ln, this is nothing but 13,332 plus, when it comes this side, what will happen? Plus will come. So this is nothing but 43,570 divided by 8.314 into 1 by 298. Cy also we are substituting, that is ln 26,665 plus 67,740 divided by 8.314 into 1 by 298. So ln of this value is 9.498. Here we wrote all the values here. Then the Cx, when we calculate this, final answer will be 27.078. Here in Cy also ln of this value is 10.19, and we calculate all these things and finally we'll get the value as 16.94. Then Cy minus Cx. The Cy minus Cx is minus of 10.138. This value minus this value, that is minus 10.138. So here we have developed one equation, that is delta Hy minus delta Hx divided by R into 1 by T is equal to Cy minus Cx. So here we apply that equation. Here we have a delta Hy, that is 16,740 minus 43,570 divided by 8.314 into 1 by T. Here we have the value 10.138. This is minus, here also we'll get one minus value and both the minus will get cancelled and we'll get positive value. Here when we subtract this, we will get minus of 33,227.08. when we subtract and divide it by 8.314, we get the value of 3227.08 divided by T. And here we have the value of 10.138. Then from this 3227.08 divided by 10.138 is nothing but 318 Kelvin. That is the temperature when the vapor pressure of the X and Y liquids are equal. I hope you understood the problems. Initially, first we have to assume that we have to do by using the Closius-Clapeyron equation, we have to write the two equations, and we have to assume that the vapor pressures are equal at a temperature T. So here, since the vapor pressures are equal, this side also will be equal. So we equate and we developed an equation, and then we went to the general equation, that is ln P1 is equal to minus delta HV by R into 1 by T1 plus Cx. Then we did the calculation and we could able to find out the Cy minus Cx. And finally, when we substitute the values here, we could able to find out the value of the temperature when the vapor pressures of the X and Y liquids are equal. This is the problem. I hope you understood this problem. Next question is, the refractive index of a liquid having molar mass is 123 gram per mole is 1.552. The density of the liquid is 1.203 gram per centimeter cube. Calculate its molar refraction. The equation to find out the molar refraction is Rm is equal to n squared minus 1 divided by n squared plus 2 into m by rho. So our job is to find out or to calculate the molar refraction. Here n is given, n is 1.552, mass is given, that is 123 gram per mole, and here we have the density also given, that is rho, that is 1.203 gram per centimeter cube. So we have to substitute all these values here, that is 1.552 square minus 1 divided by 1.552 square plus 2 into mass is 123 gram per mole divided by 1.203. So when we do this calculation, we'll get the value of molar refraction, that is 32.67. When this centimeter inverse will come in the numerator, that will be centimeter cube. So the answer is 32.67 centimeter cube mole inverse. So this is the problem related to the molar refraction. And the next problem is, the viscosity of diethyl ether in millipores is 2.84 at 0 degrees Celsius, 2.33 at 20 degrees Celsius, and 1.97 at 40 degrees Celsius. Calculate the activation energy of diethyl ether for viscous flow. That is the first question, A section of the question. And the B section of the question is viscosity at 60 degrees Celsius. So this we have to find out. So what are the details given? At 0 degrees Celsius, that is at 0 degrees Celsius, when it convert to Kelvin, that is 273 Kelvin, the viscosity is 2.84 milliPOC. Then at 20 degrees Celsius, that is 273 plus 20, 293 Kelvin, the viscosity is 2.33 milliPOC. Then at 40 degrees Celsius, that is 273 plus 40, the Kelvin is 313 Kelvin. The viscosity is 1.97 milliPOC. Now, we have to find out the activation energy of diethyl ether for viscous flow. We have a relation, that is eta is equal to AE power EA by RT. From this equation, we can find out the activation energy. When we take the logarithm of this equation, ln A is equal to ln A plus EA by RT. This equation is in the form of y is equal to mx plus c, where m is the slope. So when we draw the graph, ln eta versus 1 by t, EA by R is the slope, then c is the intercept, ln A is the intercept. Therefore, at 273 Kelvin, the viscosity is 2.84 milliPOC. Here we have to find out the ln eta. Therefore, here we have calculated ln 2.84, that is 1.044, and 1 by t also we should know, that is 1 by 273 Kelvin, 0.00366. At 293 Kelvin, the viscosity is 2.33 milliPOC, and the ln 2.33 is 0.847, and the temperature 1 by 293 Kelvin is 0.00341. And here at 313 Kelvin, the viscosity is 1.97 milliPOC, and ln 1.97 is 0.678, and 1 by 313 Kelvin is 0.00319. Now, we have to find out the m value. So, when we compare the viscosities of the two liquids, the equation becomes ln eta 1 by eta 2 is equal to EA by R into T2 minus T1 divided by T1 T2. This is the equation. Here we have taken ln eta 1 as 1.044 and ln eta 2 as 0.847. Then that is equal to EA by R. T2 is 293 minus T1 is 273 divided by 293 into 273. And when we subtract 0.847 from 1.044, we'll get the value as 0.197. Then that is equal to EA by R and T2 minus T1 divided by T1 T2. When we do the calculation, we'll get the value as 0.00025. Therefore, EA by R is equal to 0.197 divided by 0.00025. Therefore, we get the answer as 778.72. That is our slope. That is the activation energy of the liquid. That is the slope. From this slope, we have to find out the activation energy. So now we have found out the slope, that is 778.72. Now, slope is EA by R. EA is equal to 778.72 into 8.314 joule per Kelvin per mole. Then the EA becomes, so when we do this calculation, the value will be 6473.6 joule per mole. answer is in joule per mole, and when we convert that into kilojoule, 6.47 kilojoule per mole. So we will divide this by 1000 to convert joule into kilojoule. Therefore, the activation energy or the viscous flow is 6.47 kilojoule per mole. That is the answer for the first part. And the second part is its viscosity at 60 degree Celsius. Now, we have to find out the viscosity. The equation is ln eta is equal to ln A plus m into 1 by T. Here we take the viscosity of any liquid. Viscosity of the liquid, that here we have taken ln of this value, that is 1 ln of 2.84, that is 1.044. 1.044 is equal to ln A plus m is 778.72 into here, that is about the 1 by T, that is 0.00366 for this is at 273 Kelvin 1 by T. For 273 Kelvin 1 by T we have taken here, that is 0.00366. Here we have taken for the viscosity of the 273 Kelvin. So here also we have taken 273 Kelvin. From this we can find out the value of ln A. The ln A is minus 1.806. So if we know all the values of ln A and we know the slope, now we can find out the viscosity, that is ln A is equal to ln A plus ln eta is equal to ln A plus m into 1 by T. Here we have to find out the viscosity at 40 degrees Celsius. 40 degrees Celsius is nothing but 273 plus 40. Viscosity we have to find out at 60 degrees Celsius. So 273 plus 40, that is 333 Kelvin. So we have to substitute all the values what we know, what we have found out, that is ln eta is equal to minus 1.806 plus 778.72 into 1 by 333 is 0.003003. So when we do the calculation, we get the value of ln eta is equal to 0.531 and eta is equal to e power 0.531. When we do this, the value of eta is 1.70 millipoise. Therefore, here the viscosity at 60 degrees Celsius is 1.70 millipoise and the activation energy which is required for the viscous flow for the diethyl ether, that answer is 6.47 kilojoule per mole. I hope you understood this problem. This is also some interesting problem. One interesting problem, and I hope you understood the question answer session what I have discussed here. With this I wind up this chapter liquid state. I hope you understood. Thank you.